When you glance up at the sun on a clear day, it feels like the most stable thing you know. It rises and sets on schedule, bathing everything in the same soft daylight you grew up with. It looks smooth, calm, almost gentle, a perfect golden disk that never seems to change. But that is a trick of distance and scale. Up close, the sun is an ocean of fire, rippling, boiling, and erupting in slow motion. The light touching your skin today began its journey long before any human built a city. Tonight, we will peel back that calm face and step into the storm beneath it to see what our familiar star is really doing. From Earth, the sun feels simple because we only ever see the thinnest possible layer, the outer skin, where light finally escapes into space. You can think of that bright surface as a kind of snapshot of processes that remain hidden from the naked eye. For most of human history, we could only stare at that featureless glare and guess. It took centuries of physics and some very daring engineering to turn those guesses into images sharp enough to show individual storms and waves on the sun itself. Now, thanks to space observatories, we can finally see this ordinary-looking yellow dwarf star as it really is, a seething ball of magnetized plasma whose moods quietly shape life here on Earth. The story of a single beam of sunlight sounds simple at first. At the deepest heart of the sun, where the pressure is crushing and the temperature is measured in tens of millions of degrees, hydrogen atoms are forced so close together that they fuse into helium. In that act, they release energy in the form of high-energy photons. You might imagine those photons streaming straight outward like neat rays, but reality is far messier. Inside the sun, light is trapped in a dense crowd of particles, bouncing and scattering like a person trying to push through the busiest subway station on Earth at rush hour. Each time a photon bumps into matter, it changes direction and often changes energy. The result is a random walk that turns a straight path into a twisted maze. Calculations suggest that it takes somewhere between 10,000 and roughly 170,000 years for the energy created in the core to work its way to the visible surface. That means the warm daylight you enjoy during a lunch break might have started its journey before the first cities were built. Once it finally reaches the surface, that same light needs only about 8 minutes to cross the empty space between the sun and Earth. The hardest part of its journey is not the vacuum of space, but the crowded interior of its own star. When that energy finally breaks free, it comes from a layer we call the photosphere, the sphere of light. This is what you see when you look at the sun safely through a proper filter. Unlike the sharp circle your eyes perceive, the photosphere is not a solid surface, like the crust of a planet. It is more like the visible top of a deep, churning ocean. If we could hover above it with an impossible camera, we would not see a smooth disk. We would see a landscape of bright and dark patches, cells, and structures constantly changing on timescales from minutes to days. Some of the most detailed views of this layer come from instruments like the Solar Dynamics Observatory, a spacecraft that stares at the sun non-stop from orbit. It does not just take pretty pictures. It watches the sun in multiple wavelengths of light, including ultraviolet bands that our eyes cannot see. Each color cuts a different slice through the sun's atmosphere and picks out gas at a particular temperature. By comparing them, scientists build a three-dimensional, time-changing view of the star's outer layers, like a doctor using different scans to see bones, muscles, and blood flow in the same patient. In visible light, high-resolution images reveal the photosphere covered in tiny bright cells called granules. Each one is a boiling convective cell of hot plasma rising in the center and cooler material sinking around the edges. A single granule can be wider than many countries placed side by side, yet it lives for only several minutes before fading and being replaced by a new one. The tops of these cells move at several kilometers per second, fast enough to generate pressure waves that ripple through the sun like sound through a bell. When you stand in the sunshine, you are feeling the averaged glow of countless numbers of these short-lived cells flickering on and off. Sprinkled across this turbulent background are darker patches we call sunspots. At first glance, they look like holes burnt into the surface, as if parts of the sun had cooled down and died. In reality, They are regions where intense magnetic fields rise up from the interior and choke off the normal convective flow. With less fresh hot plasma reaching the surface there, those regions become cooler than their surroundings, and therefore darker. Seen from space, they are still hotter than anything on Earth, but they appear as shadows in the glare of the brighter photosphere. Around them, magnetic fields twist and reconnect, storing energy that can later be unleashed as flares and eruptions. Just above the photosphere lies a thinner, more mysterious layer called the chromosphere. Its name comes from the coloured glow it reveals during a total solar eclipse, when the moon blocks the blinding photosphere and lets us glimpse the vivid red rim underneath. Observed through special filters, the chromosphere does not look like a calm shell. It seethes with fine threads and spikes of plasma that shoot upward and fall back in looping arcs. These features, called spicules, grow taller than the highest mountains on Earth and appear and vanish in just a few minutes, as if the sun were covered in constantly exploding grass made of fire. Between the chromosphere and the layer above it lies a narrow region simply called the transition region. The name sounds dull, but what happens there is anything but. In a short vertical distance, the temperature of the gas jumps from values that would already melt any material we can make on Earth to millions of degrees. This sudden temperature rise is one of the clues that lead us toward one of the biggest puzzles in solar physics: why the sun's outer atmosphere is so incredibly hot. To see that outer atmosphere in its full glory, we need to move one step further out. This is the corona, the sun's ghostly halo. During a total solar eclipse, it appears as a shimmering white crown stretching far out into space. To cameras like those on the Solar Dynamics Observatory, the corona is not just a soft glow. In ultraviolet light, it reveals great arches of plasma following invisible magnetic field lines, loops so large that our entire planet would look like a tiny dot beside them. Bright knots mark active regions where the magnetic field is especially tangled. In those places, stored magnetic energy can be released suddenly, heating the gas to tens of millions of degrees and triggering solar flares. Sometimes the magnetic field above an active region twists itself into a rope and then snaps, hurling billions of tons of charged particles outward in an event called a coronal mass ejection. Most of these blasts stream harmlessly into space, but when one is aimed at Earth, it crashes into our planet's magnetic shield and can trigger geomagnetic storms. High above the poles, those storms light up the sky with auroras, curtains of green and red that dance across the night. Lower down, the same disturbance can induce currents in power lines and pipelines, disturb radio signals, and push satellites out of their orbits. All of that begins as shifting magnetism in the sun's atmosphere that we can now watch on our screens in almost real time. The corona is also the birthplace of the solar wind, a continuous outflow of charged particles that streams away from the sun in all directions. Darker, hole-like regions seen in some ultraviolet images mark places where the magnetic field opens out into space instead of looping back to the surface. In those coronal holes, particles can escape more easily, forming high-speed streams in the solar wind. As those streams sweep past Earth, they can produce recurring waves of geomagnetic activity, a kind of low-level space weather. What looks from here like a steady star is, in reality, constantly breathing out an invisible gale. What makes this even stranger is that all of this action is happening in layers that are incredibly thin compared to the size of the sun. The photosphere is only a few hundred kilometers deep, a whisper on top of a ball of plasma more than 1 million kilometers across. The chromosphere and transition region add only a little more. The corona extends far outward, but most of its material is spread thinly over a vast volume. When you see those dramatic images of loops and arcs and flares, you are watching fine threads of magnetized gas dancing on the skin of a star whose true bulk remains hidden below. For a long time, that hidden bulk was completely inaccessible. We could measure the sun's mass and radius. We could infer its internal structure from physics, but we could not see beneath the surface. The granular pattern of the photosphere and the waves it launches change that. Those waves travel through the interior, bounce, reflect, and emerge again at the surface, slightly altered by the conditions they have passed through. By carefully tracking how the surface ripples rise and fall, scientists can reconstruct a picture of the flows and structures deep inside, a field of study called Helioseismology. Put all of these layers and phenomena together, and the calm disk you grew up drawing in your school notebooks begins to look very different. The sun is not a static backdrop in the sky. It is an evolving system, sculpted by gravity, driven by nuclear fusion, and tangled up in its own magnetic fields. Those fields create spots, flares, eruptions, winds, and waves that do not stop at the edge of the star. They reach across space to touch Earth's magnetic cocoon, to flicker through our atmosphere, and to tug gently on the technology we increasingly rely on. Yet for all that we have learned from missions like the Solar Dynamics Observatory, from eclipse chasers, and from decades of theoretical work, a straightforward question still lingers. How can something that looks so steady from 93 million miles away be this turbulent and changeable up close? And how much of that hidden volatility is already steering the weather in space that our modern world depends on? If the sun were only chaotic, there would be nothing to predict, and our worries about it would be simple. It would be a distant storm we could never understand or plan for. The unsettling truth is almost the opposite. Beneath the boiling details of granules, flares, and loops, the sun follows a slow, patient rhythm. Your entire life, your power grid, your internet, your satellites, all of them have been quietly riding on a cycle you almost never hear about. Once you see that rhythm, you start to notice the sun's mood swings everywhere, and you start to wonder how much of what we call random is really just us being dragged along by a magnetic heartbeat. The easiest way to see that heartbeat is to count spots. For a long time, people believed the sun was a perfect, unblemished sphere. Early telescopic observers in the 1700s and 1800s started sketching dark patches that appeared and disappeared on its face. Some were scolded for suggesting the sun might be flawed. Others were not taken very seriously. Then one German pharmacist, Samuel Heinrich Schwabe, quietly watched and counted sunspots for decades. He was not trying to rewrite solar physics. He was looking for a small planet that he thought might be hiding near the sun. Instead, he stumbled onto a deeper pattern. When Schwabe plotted his spot counts over the years, a wave emerged. The number of spots rose and fell roughly every 11 years. Sometimes the peaks were high and crowded with spots, sometimes more modest, but the pattern was unmistakable. This was the first clear glimpse that the sun does not just flicker randomly. Its magnetic activity waxes and wanes like a heart that beats on a scale longer than any human memory. Today we call this the solar cycle, and we still count those spots and track that 11-year rise and fall. Sunspots themselves are more than just convenient markers. Each one marks a place where magnetic field lines punch through the surface and kink the normal flow of plasma. When there are many spots, it means the sun's magnetic field is tangled and strong. Flares and coronal mass ejections become more common. The corona bristles with bright loops and active regions. In times of few spots, the magnetic field is more settled, and the sun's outer atmosphere looks simpler and quieter. So when we say the solar cycle is rising toward a maximum, what we really mean is that the entire magnetic skeleton of the star is moving into a more chaotic posture. Deep under all of this, something even stranger is happening. The sun's magnetic field does not just get stronger and weaker. Over about 22 years, it flips. The north and south magnetic poles slowly swap places. If you could watch a little compass floating just above the solar surface, it would point in one direction for about 11 years, then gradually reverse. Together, the 11-year sunspot cycle and the 22-year magnetic cycle form a kind of nested rhythm. Every time you hear that the sun is approaching another maximum, you are really hearing that its enormous internal dynamo is winding its field up toward another flip. You live inside the influence of that dynamo. During solar maximum, when the star is magnetically excited, Earth's environment changes in subtle but important ways. The solar wind tends to be stronger and more variable. The number of high-energy particles raining down along our magnetic field lines increases. Auroras become more frequent and can wander to lower latitudes, turning night skies green and red in places that rarely see such displays. For people on the ground, these changes are mostly an awe-inspiring light show. For technology in orbit, and for systems that depend on radio and satellite signals, they are something more like a stress test. Picture a ring of satellites circling Earth. Some provide navigation signals, some monitor weather, some relay communications. They exist in a delicate balance between gravity pulling them inward and orbital velocity flinging them outward. Now imagine the upper atmosphere puffing up and becoming denser because energetic particles from a stormy sun are heating it. Those particles do not have to reach the ground to matter. They increase drag on satellites, slowing them slightly, lowering their orbits. Over time, that drag must be corrected with thrusters. If the storm is strong enough and preparation is poor, some satellites can even re-enter sooner than planned. At the same time, radio waves that normally bounce smoothly off layers of the ionosphere can be scattered or absorbed by sudden surges of solar radiation. High-frequency radio communication over long distances can fade or become noisy. Navigation signals can shift or briefly become less accurate. Airlines that rely on long polar routes sometimes adjust their flight paths during strong solar events, not because passengers will feel anything dramatic, but because communication and radiation levels at high altitude can be affected. Astronauts on the International Space Station and beyond watch solar forecasts the way sailors once watched the horizon, because a large flare can raise their radiation exposure in ways mission planners take very seriously. In quieter solar years, these risks do not disappear, but they change in character. The solar wind is more gentle, the frequency of large eruptions drops, auroras retreat toward the poles. There is less dramatic space weather. It might seem tempting to think of these years as simply safer, but the reality is more nuanced. The sun also provides a shield of sorts. Its outflowing wind and magnetic field help push back some of the high-energy particles that arrive from outside our solar system, cosmic rays born in distant supernova explosions. When the sun is magnetically quieter, that shield can weaken, and the flux of cosmic rays near Earth can increase subtly. The balance between solar storms and cosmic rays is another rhythm we are still learning to read. All of this is solid, measurable physics. We can track the solar cycle by counting spots, by monitoring X-ray fluxes, by watching the solar wind. Where things become more controversial is when we ask how this long cycle might connect to climate and to life. History offers some intriguing coincidences. In the 1700s, there was a period known as the Maunder Minimum, when sunspots were extremely rare for several decades. This lull lines up with a time often called the Little Ice Age, when parts of Europe and North America experienced colder than usual winters, frozen rivers, and persistent cool summers. It is very tempting to draw a clean arrow from fewer spots to less solar activity to colder weather. Some reconstructions of solar output do suggest that the sun was slightly dimmer during that minimum. Climate models show that even small changes in incoming solar energy can shift circulation patterns and regional temperatures. At the same time, climate is influenced by volcanic eruptions, greenhouse gas levels, ocean circulation, and internal variability. Sorting out which factor did what in the past is hard. Many researchers see a modest solar contribution to the Little Ice Age, but it is only one piece of a complex picture. The same caution applies when we look at modern climate change. The solar cycle is still beating, but direct measurements of the sun's total brightness since the late 1970s show only small fluctuations that follow that 11-year pattern. They do not show a large upward trend that could explain the strong warming of recent decades. Instead, the dominant driver there is the rise in greenhouse gases in our own atmosphere. When you hear people say that climate change is just the sun getting stronger, they are compressing a subtle reality into a simple story that does not match the data. The sun does influence climate, especially on regional and short timescales, but it is not the main cause of the rapid warming we are seeing now. Outside of climate, there have been studies claiming links between the solar cycle and all sorts of phenomena, from earthquakes to stock markets to human health and mood. Some animals seem to respond to changes in geomagnetic activity. There are suggestions that heart rate variability, stroke incidence, or sleep patterns may show small correlations with solar activity. These ideas are intriguing and sometimes get amplified in popular media, but they are often fragile. Samples can be small. Confounding factors can be hard to rule out. Repeated studies do not always confirm the same effects. At this stage, it is safer to say that the Sun's magnetic rhythm may leave faint fingerprints in many systems, but those fingerprints are subtle and easily overwhelmed by larger forces. Where the influence is obvious and immediate is in what we now call space weather. In the same way that meteorologists track air pressure, humidity, and wind to forecast storms, space weather forecasters track sunspot numbers, X-ray emissions, and solar wind parameters to warn of geomagnetic storms. Spacecraft parked at special gravitational balance points ahead of Earth, such as the one called the L1 point, act as sentinels. They measure the speed, density, and magnetic orientation of incoming solar wind. When those measurements shift into a pattern known to precede strong geomagnetic disturbances, alerts go out to power companies, satellite operators, and airlines. Even with all that preparation, we are still learning how to live with a star that does not always behave. Some cycles are mild, others produce more large flares and coronal mass ejections than expected. The timing of peaks can shift a little. Models that try to predict the strength of a coming solar maximum sometimes disagree. Part of the challenge is that we do not yet fully understand how the Sun's internal magnetic field is generated and how it flips. Deep inside, differential rotation, convection, and magnetic feedbacks are weaving a pattern that reaches the surface years later. We see the skin, we infer the beating heart, but we do not yet have a complete map connecting the two. Imagine standing on a beach and watching waves. You can count the small waves that reach you. Notice that sometimes they come faster, sometimes slower. With practice, you might notice a larger pattern, a set of big waves every few minutes. But the full story of those waves lies in winds far out at sea, in the shape of the seafloor, in distant storms you cannot see from shore. That is where we are with the solar cycle. We can count the magnetic waves rolling over the surface. We can sketch a rough cycle, but the distant storm, the deep dynamo that is setting the rhythm, remains partially hidden. This is where the earlier idea of listening to the sun becomes more than a poetic phrase. The same ripples in the photosphere that let us do helioseismology carry information about flows of plasma and tunnels of magnetic field deep within the star. By combining surface observations, magnetic maps, and these internal soundings, scientists are slowly piecing together a more complete picture of the solar engine. The goal is not just to satisfy curiosity, although that would be reason enough. It is to gain the kind of understanding that lets us say, with some confidence, when the next peak in activity will arrive, how strong it might be, and what kind of storms it could send our way. As we work toward that goal, you and I are living through only a few cycles, just a small sample of the Sun's longer-term behaviour. Geological and astronomical evidence hint at even larger scale variations over centuries and millennia. Sometimes cycles are weaker, as during the Maunder minimum, sometimes stronger. There may be nested rhythms we have not yet fully recognised, because our detailed measurements only go back a few decades. That uncertainty should not paralyse us, it should sharpen our attention. Our civilization has grown up assuming that the Sun's changes are minor compared to the stability we enjoy. The more we learn, the more that assumption starts to look like another comforting story. So we are left with a star that hums along in long cycles, reshaping its own magnetic field, breathing out gusts and gales of plasma that wash over our small world, nudging our climate, lighting our skies, and occasionally threatening our technology. We can count its spots and watch its storms, but until we know how its rhythms are born, we are really reading only the handwriting on the surface. To go deeper, we have to stop just looking at the sun and actually listen to it, to treat it like a musical instrument whose vibrations carry secrets from the hidden interior. If you stand in a concert hall while an orchestra is warming up, you can feel the air thicken with sound, even before the music properly begins. Each instrument sends out vibrations that collide, blend, and interfere with one another. If you had sensitive microphones and a powerful computer, you could in principle work backward from the sound and figure out which instruments were playing, where they were located, and how the Hall itself was shaped. That is almost exactly what solar physicists decided to do with the Sun. They would not just look at the surface, they would listen to the tiny ripples racing across it, and use those vibrations to map a place no probe can reach. At first, this idea sounds impossible. Sound waves need a medium, and space is almost entirely empty. There is no air between Earth and the Sun to carry a tune. But inside the Sun, and in its outer layers, there is plenty of material for waves to travel through. The plasma in the solar interior behaves like a compressible fluid. When hot material rises and cooler material sinks, it creates pressure fluctuations. These fluctuations launch waves that slosh back and forth under the surface. The Sun is constantly ringing with these pressure modes, much like a giant star-sized bell that never stops being struck. We do not hear this ringing with our ears. The frequencies are mostly too low, and the medium is too different. Instead, the waves subtly lift and lower patches of the photosphere. Imagine the surface of the Sun rising and falling by a few dozen meters, over and over, in complex patterns that repeat thousands of times per day. To the naked eye, that motion is invisible against the blinding light. To sensitive instruments that track Doppler shifts, tiny changes in the color of light from moving gas, those motions become a clear signal. By staring for hours and days, telescopes record an intricate dance of up and down that encodes the interior structure. This is the heart of helioseismology, the art of using solar quakes to image the inside of the star. Each wave mode has a characteristic frequency and penetrates to a particular depth. Some skim near the surface, others dive deep, curve through the interior, and return. By teasing apart which frequencies are present and how strong they are, scientists can infer the temperature, density, and rotation rate in different layers. It is a bit like listening to a drum and figuring out how thick the drum head is, what it is made of, and how the frame is shaped, all from the sound alone. What these solar vibrations reveal is a layered interior that mostly matches what theory predicted, but with important twists. At the very core, nuclear fusion converts hydrogen into helium and releases energy. Surrounding that is a radiative zone where energy moves outward mainly through radiation, with photons bouncing and scattering. Further out, in the outer third or so of the Sun, lies the convective zone, where hot plasma rises and cooler plasma sinks in great rolling cells. Helioseismology confirms the boundaries between these layers and shows how the rotation changes with depth, faster in some latitudes, slower in others, twisting the magnetic field over time. One of the surprises from helioseismology is a region near the base of the convective zone where rotation changes sharply. This shear layer is a prime suspect in the generation of the Sun's magnetic field. It is where differential rotation and convection interact in ways that can stretch and fold magnetic field lines, amplifying them into the global field that later pokes through the surface as sunspots. The fact that we can point to this hidden layer with confidence is a testament to how much information is carried by those surface ripples. There is another kind of wave at work too. In addition to pressure waves, or P modes, the Sun can support gravity waves, sometimes called G modes. These involve fluid parcels bobbing up and down under the influence of buoyancy deeper in the star. Detecting them directly is harder, and their signatures are more subtle, but they promise even more detailed information about conditions in the core. The search for clear G-mode signals has been a long-running quest, and every possible hint is checked and debated. It is one more reminder that even with our best tools, a star does not give up its secrets easily. To make the solar music more tangible, some researchers have taken measured oscillations and shifted their frequencies into the human hearing range. When played through speakers, the Sun sounds like a deep, complex hum, punctuated by higher tones. It is not just a gimmick. Translating the data into sound helps us appreciate that we really are listening to a physical object vibrate. Each tone is a message from a different depth, a different path taken by a wave in a plasma ocean, hundreds of thousands of kilometers below the surface. Now carry that sense of vibration outward from the interior to the atmosphere. The same convection that makes granules on the photosphere and launches waves inward also sends waves upward. Some of these waves travel through the chromosphere and into the corona. They twist and shake magnetic field lines, driving plasma back and forth. In videos, you can sometimes see loops sway and jiggle. Those motions are not just surface decoration. They may be carrying energy that can be turned into heat. Here we run into one of the longest standing puzzles in solar physics, the so-called coronal heating problem. The puzzle begins with a simple comparison. The visible surface of the Sun is about 6,000 degrees. Just above it, temperatures in the chromosphere and transition region rise, and then, in the corona, they leap to millions of degrees. It is as if you stepped away from a campfire and found that the air got hotter as you moved farther from the flames. That defies ordinary intuition. In most familiar settings, heat flows from hot to cold, not the other way around. We know the energy has to come from below because the corona has no internal power source of its own. The question is how that energy gets transported and converted into random thermal motion of particles high above the surface. Several broad ideas have been explored. One involves waves, another involves tiny magnetic reconnection events called nanoflares. Most likely, more than one mechanism contributes, possibly with different processes dominating in different regions. The Sun is rarely kind enough to give us a single neat answer. The wave-based idea goes like this. Convection in the lower atmosphere and interior constantly jostles magnetic field lines. That motion launches waves that travel along the fields, like vibrations along a plucked string. Some of these waves, known as alphern waves, involve the plasma and magnetic field moving together. If these waves can propagate into the corona without being damped too quickly, and then dissipate their energy there, they could heat the coronal plasma. The challenge has been to show that enough wave energy actually makes it into the corona and is absorbed in the right way. Observations from space telescopes do show waves and oscillations all over the solar atmosphere. Loops sway, brightness features slide along field lines, spectral lines broaden in ways that suggest unresolved motions. The problem is that measuring the full energy budget is difficult. Some waves may simply pass through, others may reflect, still others may turn into different kinds of waves as they move through regions with changing density and magnetic strength. Theoretical models and numerical simulations continue to explore how much heat this zoo of waves can provide. The nanoflare idea comes from the magnetic side. We know that large flares occur when twisted magnetic field lines snap and reconnect, converting magnetic energy into heat and kinetic energy. What if the corona is constantly experiencing much smaller versions of this process, too tiny to see individually with current instruments? Each nanoflare would release a small packet of energy, heating local plasma. If they are frequent enough and distributed widely, their combined effect could maintain the high coronal temperature. In this view, the corona is not quietly heated by a smooth wave bath, but is instead peppered with countless miniature explosions. There is some evidence for this. High-resolution observations show sudden brightenings in small regions, hints of tiny jets, and turbulent motions that are hard to explain without some kind of impulsive energy release. Spectra reveal plasma at temperatures that are difficult to maintain with only gentle heating. Yet just as with waves, many details remain murky. How often do nanoflares occur? How much energy does each carry? How does the magnetic field tangle at small scales? These questions push us up against the limits of both our instruments and our models. While we continue to argue about the exact mix of waves and nanoflares, there is one product of the corona that we know intimately, the solar wind. This continuous outflow of particles flows away from the Sun at speeds of hundreds of kilometers per second. In fast wind streams, that speed can exceed 700 kilometers per second. The wind carries with it not only charged particles, mainly protons and electrons, but also an embedded magnetic field. As the Sun rotates, that field gets wound into a spiral pattern, a huge rotating structure, sometimes called the Parker spiral, after the scientist who described it. Close to the Sun, the corona is dense and hot. Farther out, the gas expands and thins. Somewhere in between, the outflow speed surpasses the local speed of sound in the plasma and keeps accelerating outward. The details of that acceleration are linked to the same processes that heat the corona. If waves or nanoflares energize particles, those particles can help drive the wind. Regions with open magnetic field lines, such as coronal holes, tend to be the source of fast wind. Regions with closed loops tend to produce slower wind, at least in the simplest picture. By the time the solar wind reaches Earth, it has filled space with a tenuous plasma through which planets and spacecraft move. When this flow meets Earth's magnetic field, it is diverted and shaped, forming a bow shock, a magnetopause, and a long magnetotail downstream. Changes in the speed, density, and magnetic orientation of the wind can trigger geomagnetic storms or calm conditions. All of that space weather starts at the Sun, in a corona whose basic heating mechanism we are still trying to pin down. You might ask why this matters so much. The corona is far away. Its particles rarely reach the ground. Our atmosphere and magnetic field protect us from most of the direct effects. But our technology does not live only on the ground anymore. It lives in orbit and in the ionosphere. Satellites, communication links, navigation systems, and even some long power lines are directly exposed to the changing moods of that hot, thin plasma. If we want to forecast space weather with the same confidence we now forecast rain, we need to understand the engine behind the solar wind, not just its output. There is also a deeper scientific itch here. The Sun is the closest star we will ever study in such fine detail. If we cannot fully explain why its corona blazes so much hotter than its surface, what else are we missing about other stars? Many stars show their own forms of coronae and winds. Some possess flares much more energetic than anything our Sun has ever thrown. Some bathe their planets in intense radiation. The physics that solves the coronal heating problem here will likely echo across the wider universe. So we listen. We listen to the hum of P modes and the whisper of possible G modes, reading the interior. We watch loops sway and small brightenings flash, looking for traces of waves and nanoflares in the corona. We send instruments to watch the solar wind where it is born and where it flows past our world. Each new observation is both a clue and a test, revealing which ideas survive and which must be discarded. Along the way, we are learning something humbling about our own reasoning. Again and again, the Sun has shown us that our first explanations, the ones that seem obvious, are often wrong. The star that looked perfect turned out to be spotted. The surface that looked solid turned out to be fluid. The light that seemed to come straight from the core turned out to wander for ages. The halo that seemed too faint to matter turned out to dominate the space between planets. If we can misread so many signs from the nearest star with all our instruments, it raises an unsettling question that will follow us as we chase the next mysteries written in its light. If the Sun can be so thoroughly misunderstood, even when it is right above us, what happens when we add our own expectations on top? Over and over, scientists have looked toward that bright disk, already convinced they knew what must be there. Sometimes they saw what they wanted so clearly that they even sketched it, measured it, and defended it, only to watch it evaporate under better data. The Sun is not just a physical object. It is also a mirror for our habits of belief, our willingness to bend reality to fit a neat theory. Before we travel to other stars and imagine their worlds, it is worth sitting a little longer with the ways we have misread our own. The most famous phantom to haunt the space near the Sun was a planet that never really existed. In the 19th century, astronomers believed Newton's laws gave them a perfect clockwork model of the solar system. For most planets, that model worked beautifully. They could predict positions and orbits with impressive accuracy. Then there was Mercury. Its orbit precessed, meaning the point of closest approach to the Sun drifted over time. Most of that drift matched the Newtonian calculations. A stubborn little extra remained, a mismatch of a few arc-seconds per century that would not go away. To many scientists, the idea that Newton's gravity might be incomplete was too drastic. A much more comfortable explanation presented itself. Perhaps there was another planet inside Mercury's orbit, tugging on it and disturbing its path. If that unseen world were small and close to the Sun, it would be very hard to see in the glare. The idea felt satisfying. It kept the grand theory intact and blamed the anomaly on missing matter. They gave the invisible planet a name, Vulcan, and began to search. Once Vulcan had a name and a predicted orbit, a strange thing happened. Observers began to report it. A few astronomers and amateurs claimed they had seen a small point of light crossing near the Sun during eclipses or transits. These reports were often inconsistent, but they were collected and debated seriously. Patterns were drawn, orbits were proposed, textbooks mentioned Vulcan, charts were printed with a dotted circle marking where the hidden planet should be. It is easy, from a modern vantage point, to smile at this. It is harder to admit how natural it was. From their point of view, the logic seemed solid. Newton's gravity worked everywhere else. The tiny mismatch in Mercury's orbit looked like something caused by an extra mass. Human perception is suggestible, especially when looking at faint spots near a blinding light. An observer who half expects to see Vulcan might interpret any small dot or internal reflection in the telescope as confirmation. The story they had in their minds guided their eyes. Little by little, the non-existent planet took on a kind of reality in the scientific culture. The spell broke only when a new theory came along that did not need Vulcan at all. Einstein's general theory of relativity replaced Newton's gravity with a picture of curved space-time. In that picture, Mercury's orbit naturally precesses more than the Newtonian prediction when it moves through the intense curvature near the Sun. When the new equations were applied, the stubborn mismatch disappeared. There was no missing mass to explain. Vulcan was not required. The extra planet evaporated, leaving behind a cautionary tale about how strongly we cling to familiar frameworks. This episode matters for more than historical curiosity. It shows how the Sun can become a projection screen for our theories. When data do not fit, we are tempted to add a hidden object that preserves the rules we like, rather than question the rules themselves. The same pattern has repeated in other contexts. We have added epicycles to orbits to save circular motion, invented ether to carry light waves, and seen canals on Mars that were really optical illusions and human pattern seeking. Each time, the heavens held still. Our minds did the twisting. You do not have to go as far as a fictional planet to see the Sun play tricks with vision. On cold winter nights, many people have looked up at the moon surrounded by a pale ring of light and taken it as a sign of coming weather. This ring, often called a halo, can also encircle the Sun, though it is easier and safer to notice around the dimmer moon. It looks like a perfect circle, drawn by some cosmic hand. In reality, it is sunlight or moonlight refracted through tiny ice crystals high in the atmosphere, usually in cirrus clouds. Those crystals act like millions of tiny prisms. When light enters them at certain angles, it is bent and emerges at a fixed offset from its original direction. From the ground, we see brightened light at the angle where many refracted rays converge. That angle is about 22 degrees from the Sun or Moon, which is why halos have a characteristic size. Nearby, you might see bright spots called sundogs, or pillars of light, when crystals are oriented in particular ways. None of these structures exist as solid rings or pillars in the sky. They are geometry and perspective, playing with scattered ice. The same principle operates in other worlds. On Mars, cameras have photographed delicate halos around the Sun, created by ice crystals in the thin Martian atmosphere. To someone standing on the dusty surface, that halo might carry emotional weight or suggest omens, just as it did to humans on Earth before we understood optics. Once again, the Sun becomes both a physical light source and a canvas for stories. Our explanations improved only when we combined careful observation with experiments on Earth, shining light through crystals and matching the patterns. Eclipses add an even more dramatic layer of illusion. During a total solar eclipse, the Moon passes exactly in front of the Sun, revealing the corona as a glowing crown around a black disk. The sky darkens, temperatures drop slightly, animals change their behaviour. It feels as though the Sun itself has been wounded. In early cultures, this sudden disappearance of the light often inspired myths of devouring dragons or angry gods. Even today, the emotional shock of midday darkness can make a thoroughly prepared scientist feel something beyond calculation. Yet the geometry behind a total eclipse is quietly precise. The Sun is about 400 times wider than the Moon and about 400 times farther away. That coincidence makes them appear almost the same size in our sky. Because both orbits have small tilts and are not perfect circles, total eclipses are relatively rare from any given place. When they do occur, the Moon's apparent size can be slightly larger or smaller than the Sun's. If it is smaller, the result is an annular eclipse, with a ring of bright photosphere still visible. If it is larger and the alignment is exact, the disk of the Sun vanishes completely and the corona blooms. That corona, once revealed, used to be a source of confusion in its own right. Before scientists knew it was a hot outer atmosphere, some suspected it might be a kind of optical effect in Earth's air, or a reflection, or even matter associated with the Moon. Only repeated observations from different locations, combined with spectroscopy that showed emission lines belonging to highly ionized atoms, finally made it clear that the corona belongs to the Sun. Eclipses forced us to separate what our eyes felt from what the data said. Beyond halos and eclipses, comets near the Sun have sparked some of the most intense misreadings. A comet that swoops close to the Sun can appear to skim its surface or even plunge into it from our perspective. In reality, most so-called sun-grazing comets swing around the Sun on highly elliptical orbits, some surviving to return, others breaking apart under the tidal stresses and heat. Space-based observatories that watch the Sun in narrow fields of view often capture these comets as bright streaks that end near the solar limb. When such footage circulates without context, it feeds dramatic claims. You may have seen videos online that claim massive objects are orbiting just above the Sun's surface, or that artificial structures are drawing energy from it. Many of these clips show ordinary coronal loops, flares, or passing comets, misinterpreted or mislabeled. Our brains are good at seeing intention in patterns, especially when the image is noisy and high contrast. A looping prominence can look like machinery. A comet's tail shrinking as it evaporates can look like a craft docking. Without training, it is easy to mistake instrument artifacts for strange objects. Scientists are not immune to illusion either. When the first space-based coronagraphs watched the region around the Sun, they revealed countless small blobs and jets. Sorting out which were actual mass motions and which were stray light, cosmic ray hits on detectors, or internal reflections took time and careful calibration. Early catalogues of coronal mass ejections included events that later turned out to be something else. Over years, teams learned how to correct their instruments and interpret what they saw. Humility and repeated checks were the only antidotes. In a way, the Sun encourages overinterpretation. It is dazzling yet hard to look at directly. It is tied to deep fears and hopes in almost every culture. When something unusual appears near it, whether a halo, a bright point, or a brief flicker, we are primed to see meaning. We look for hidden planets, signs, warnings, messages. The real physics does not need any of that to be magnificent. Light refracting through ice, plasma following magnetic field lines, comets disintegrating under heat. All of these are rich stories on their own. The trick is to let them be what they are, rather than what we wish them to be. If this were only about correcting old mistakes, it would be a finished chapter. But the habits that produced Vulcan and misread comets are still with us. Today we point sensitive telescopes at distant stars and watch them dim slightly as planets pass in front. We pass tiny variations in starlight to infer atmospheres, clouds, and even hints of possible biology. The farther we push this technique, the more we rely on interpreting patterns in light from objects we will never visit. The risk of seeing canals on Mars where there are none becomes the risk of seeing life on an exoplanet where there is only chemistry. Our own Sun is the training ground for that work. Here we can test how often our models line up with reality. We can compare the signatures of flares, spots, and eruptions in sunlight with direct imaging and in situ measurements. When we see a star like our Sun undergo a strange dimming or brightening, we can ask whether some solar analogue might be at play. Was there a large sunspot group rotating into view? Was there debris? Was there a temporary veil of dust? Each time we catch ourselves jumping to the most exotic explanation first, the story of Vulcan whispers a warning. The deeper lesson is not that we should distrust our senses completely. It is that we should treat the sun as both a laboratory and a mirror. It shows us physical processes that are hard to replicate on Earth. It also shows us how easily we wrap those processes in comforting narratives. Once you see that double role, a new question begins to form. If this one ordinary-looking star can host so many illusions in its light, what happens when we put ourselves under the glow of very different suns, with very different tempers and colours, and try to imagine what kind of worlds could survive there? Put yourself on another world for a moment. Not a science fiction city with glowing towers and sleek ships, just a rocky ground under your feet and a sky above you, but with a different star in it. Maybe the light is redder and dimmer, so midday feels more like a deep sunset. Maybe there are two suns, one bright and one pale, circling each other in a slow dance. Maybe the star is swollen and bloated, filling half the sky in a way that feels both magnificent and terrifying. The simple rhythm of day and night that you grew up taking for granted starts to wobble and fracture. Under those strange suns, what you call normal would be a fragile, temporary arrangement at best. Let us start with the most common stars in our galaxy, the small, cool red dwarfs. They are dim compared to our sun, and because they shine more weakly, any planet that wants liquid water on its surface has to huddle close. That closeness has consequences. Gravity from the star can lock a planet into a state where the same side always faces the light, the way our moon always shows one face to Earth. One hemisphere bakes under permanent day, while the far side sits in endless night. Between them lies a band of eternal twilight, a narrow strip where temperatures could be more moderate. Imagine standing in that twilight zone. The star is huge in the sky, glowing a deep red-orange. Shadows are long and strange. The horizon toward the day side glows brighter. The horizon toward the night side fades into a cold darkness speckled with stars. If the planet has a thick enough atmosphere, winds might move heat from day to night, softening the extremes. The climate there would not be impossible. But red dwarf stars have another trait that complicates the picture. Many of them flare, often and violently, especially when they are young. Flares on some red dwarfs make our sun's worst tantrums look modest. These stars can release bursts of high-energy radiation that would dwarf any solar storm we have recorded here. If you lived on a planet close to such a star, every so often the sky would flash with harsh ultraviolet and X-ray light. The planet's upper atmosphere would be hammered, its chemistry altered. Over long times, repeated flares and associated particle blasts could strip away air and water, especially if the planet's magnetic field were weak. For any life trying to emerge on the surface, the star that warmed it would also be a constant source of danger. Some scientists have argued that life under these conditions might retreat under rock, into oceans, or beneath thick ice, where radiation is less severe. Others point out that red dwarfs live for incredibly long times, far longer than our sun will. That long, dim life might give biology many opportunities to adapt and persist, if it can survive the early stormy youth of the star. Either way, the picture is clear. Under a red dwarf, habitability is a narrow, precarious compromise between warmth and flare-driven violence. The idea of a stable, gentle midday sky becomes something you have to fight for. Now swing your imagination in the opposite direction, to massive hot blue or white stars. They shine with fierce intensity, pouring out light and high-energy radiation. Their habitable zones, the regions where a planet could orbit with temperate conditions, lie far out. At those distances, day and night might feel more familiar, with suns that are bright but not enormous in the sky. The problem here is not flares, though these stars can certainly be variable. The deeper issue is time. Massive stars burn their fuel quickly. Their main sequence lifetimes can be only a few tens of millions of years, sometimes even less. On human scales, Tens of millions of years sound like an eternity. On evolutionary scales, it is short. On geological scales, it is the blink of an eye. Life on Earth took billions of years to go from simple cells to complex multicellular organisms walking on land. Around a very massive star, the star itself would race through its life, swell into a giant, and end in a cataclysmic supernova before similar complexity had much chance to evolve. Even if simple life could gain a foothold in those rapidly changing environments, the clock would always be ticking toward a violent end. When such a star finally dies, it does not go quietly. A supernova floods nearby space with intense radiation and energetic particles. If a planet were close enough, its atmosphere could be stripped or severely altered. Even worlds farther out could experience mass extinctions if the burst were intense and well aimed. The idea that a star could suddenly end the story for an entire biosphere is not speculation. The history of our own galaxy includes many such explosions. We have been spared only because our sun is not massive enough to die that way, and because we live in a relatively calm region, far from crowded star-forming clusters where such giants are common. Between tiny red dwarfs and hulking blue giants lies a more familiar family of stars, the yellow and orange types that include our Sun. They live for billions of years, long enough to allow complicated chemistry and long evolutionary stories. Their habitable zones are at distances where tidal locking is less likely. Their flare activity is moderate compared to the most violent red dwarfs, especially as they age and settle. Within this band of stellar types, the chances of a planet enjoying a long era of relative stability are higher. Even here, though, not all stars are as well behaved as ours. Astronomers have seen stars very much like the Sun that produce what are called superflares, eruptions hundreds of times more energetic than the strongest solar flares in the historical record. If our Sun were to unleash such a blast, the effects on Earth's technology, and perhaps on our atmosphere, would be profound. Why some stars flare this way while others do not is still a subject of study. It may be connected to how fast they rotate, to the presence of close-in giant planets, or to details of their magnetic dynamos. The unsettling lesson is that even among stars that look like comfortable twins of our own, there are more dramatic personalities. Then there are the systems with more than one star. Binary and multiple star systems are common in our galaxy. Some have two suns orbiting close together, with planets circling far outside, feeling the combined gravity as if it came from a single source. Others have wide binaries, where planets circle one star while the other traces a distant path in the background. In still other arrangements, planets weave complex paths in gravitational fields that shift over time. The result for any inhabitants would be sky shows unlike anything we experience. Picture standing on a world that circles a close pair of suns. Sometimes they would rise together, casting double shadows. Sometimes one would set while the other remained, tinting the sky in changing colours. The total light bathing the planet would vary as the stars moved, altering seasons in patterns that might be more complex than our familiar yearly cycle. On worlds where a planet loops around one star while the companion star swings through the sky on a long orbit, there could be eras where the second sun is bright and close, and eras where it is a pale, distant point. Climate patterns would respond to these slow, wandering rhythms. Not all such systems are hostile to life. Computer models show that under the right conditions, planetary orbits in binaries can be stable over long times, but the margins can be thin. Slight changes in initial conditions or later gravitational nudges from passing stars can destabilize orbits and send planets drifting inward or outward. The picture that emerges is one where some configurations offer peacefully repeating double sunrises, while others are precarious balancing acts in which entire climates may shift if orbital resonances stack up in the wrong way. Even in single-star systems, the broader galactic neighbourhood matters. Stars born in dense clusters share their first few 100 million years with many siblings. Close passes between stars in such clusters can perturb planetary orbits. Nearby supernovae can bathe young worlds in radiation, altering atmospheres or stripping them before life has a chance to get going. Over time, clusters disperse and stars migrate to quieter regions. Our Sun seems to have had such a youth long ago, and now drifts in a relatively sparse part of the Milky Way. It is not near the violent star-forming regions or the crowded galactic centre. That calm backdrop is another stroke of luck for a planet that wants steady conditions. Bring all of this back to Earth, and you begin to see our situation in sharper relief. We orbit a star that is massive enough to flood its planets with useful light, but not so massive that it races through its life. Its main sequence lifetime is on the order of 10 billion years, and we find ourselves about halfway through that span. We sit at a distance where liquid water can exist over geologic time, far enough to avoid tidal locking, close enough to avoid a permanent deep freeze. Our sun flares and storms, but not as often or as violently as many stars of other types. Its cycles are detectable, and at least somewhat predictable. For billions of years, that combination has allowed oceans to remain, continents to drift, and climates to change at a pace that life could sometimes adapt to. There have been mass extinctions, yes, but not because the sun abruptly doubled its output or exploded. Instead, they have been driven by impacts, volcanic outpourings, and internal planetary processes. Even the faintness of the young sun, which shone less brightly for the first billions of years, lined up with greenhouse gas levels to keep Earth mostly above the freezing point of water. It is a delicate balance, forged out of many moving parts. On top of that, our star's relative quiet has given human civilization room to grow. We built radios, satellites, and power grids during a stretch of time when no truly extreme solar superstorm struck. We extended electrical wires across continents and laced orbit with metal, without ever having to live through a storm that destroyed a significant fraction of that infrastructure in one blow. We came to think of the sun as a constant background. Weather meant clouds and wind, not changes in the star itself. That habit of mind is understandable. It is also a little dangerous. If you transplanted our current technology to a planet around a more volatile star, you would have to design everything differently. Satellites would need heavier shielding. Communication systems would rely more on fibre and buried lines than on long-range radio reflections. Power grids would be broken into smaller, more resilient segments to avoid cascading failures. Humans might spend more of their time underground or in shielded habitats, not because the surface is instantly fatal, but because the daily radiation background is more punishing. The rhythms of culture and work would bend to the moods of the star, as surely as ancient farmers once bent to the seasons. Seen from that angle, our sun begins to look like a rare and generous partner. It is not perfect. It can and does throw storms at us. But it sits in a sweet spot of mass, age, composition, and variability that has made a complex biosphere and a technological civilization possible. We do not yet know how many other stars share that mix. The search for planets in other systems has already found worlds in all kinds of strange arrangements, hugging close to red dwarfs, orbiting two suns, circling pulsars, drifting in the cold far from any light at all. Somewhere in that growing catalogue, there may be planets bathed in light as mild as ours, but we will need time and better tools to be sure. In the meantime, we can treat our sun as both a benchmark and a warning. It shows us one way a star can support life for billions of years. It also reminds us that stability is never absolute. Its cycles and storms are modest only in comparison to what other stars can do. For a civilization that now depends on fragile layers of electronics, satellites, and long transmission lines, even a single badly timed solar outburst could feel like a small taste of the harsher universes we have so far escaped. If we want to understand how special our sun really is, and how to live more safely under it, it is not enough to study it from afar. Telescopes and theory have carried us a long way, but the most revealing stories often begin when we dare to go closer, into regions we once assumed were unreachable. At some point, the only way to truly know how a star works is to send machines right into the edge of its fire and watch what happens next. The moment you decide to send a machine toward the sun, you discover that going inward is much harder than going outward. Flinging a probe to the outer planets is mostly a matter of adding speed in the right direction. Dropping something toward the star means erasing the enormous sideways motion that keeps Earth in its orbit. Our planet is racing around the sun at about 30 kilometers per second. Any spacecraft that launches from here starts with that sideways push baked in. To fall straight inward, you have to undo a lot of that motion, and undoing motion costs energy that rockets are very bad at giving. For a long time, that simple fact made missions to the inner solar system seem nearly impossible. Engineers could imagine heat shields, robust instruments, and clever communication systems. They could not see a way to cheat the tyranny of orbital mechanics. If you just point a rocket at the sun and fire, you end up in an orbit that still circles it, only slightly different from Earth's. To dive really close, you must steal energy from something else. In our case, that something is another planet. The path to the Sun runs through careful dances past Venus, using its gravity as a brake. Parker Solar Probe is the machine that finally took that dance seriously enough to fly it. The idea of a solar probe skimming the corona dates back to the 1950s, when the space age was just beginning. For decades, it lived as a sketch on whiteboards and in science fiction-like mission studies. The main obstacles were always the same. How do you get close without melting? How do you shed enough orbital momentum to really taste the inner corona? How do you keep a spacecraft alive when one side faces a blast furnace and the other side stares into deep space? The eventual answer was a combination of boldness and restraint. Designers at NASA built Parker around a heat shield unlike anything flown before, a circular slab of carbon composite more than 2 meters across and not very thick. When the spacecraft aims that shield at the sun, almost all the incoming energy is absorbed or reflected. Behind it, in the shadow, the instruments sit in a much milder environment, kept near room temperature. Wires, sensors, and solar panels peek around the edge only as much as they must, and many of them can be folded back during the closest approaches to reduce their exposure. Even with that shield, Parker could not just dive on its first orbit. It launched in 2018 and has been working its way inward over a series of loops, each one broken by a close pass by Venus. At each flyby, a little of the spacecraft's orbital energy is traded with the planet. Venus gains a tiny amount, almost unnoticeable. Parker loses some and falls closer to the Sun on its next pass. Over time, those small adjustments add up, dropping the point of closest approach to a fraction of the distance between the Sun and Earth. On those close passes, Parker moves faster than any human-made object has ever moved. At its peak, its speed approaches 700 kilometers per second relative to the Sun. In that regime, concepts like sunrise and sunset blur. The spacecraft races through the inner corona, samples the solar wind, and then swings back out again before looping inward once more. If you could somehow ride on it, you would see the Sun swell from a blinding disk to a vast, shimmering presence that fills much of the sky. Its light intense enough that even a small error in pointing the shield would be fatal. Parker is not alone in this quest. A companion mission called Solar Orbiter, built by the European Space Agency with contributions from NASA, follows a different path a little farther out. Where Parker is mostly about flying through the corona and touching the wind, Solar Orbiter carries a richer suite of telescopes and imagers. Its orbit is tilted slightly out of the plane of the planets and will gradually become more inclined, giving it a view of the solar poles that we have never really had before. Together, the two missions are like a doctor who not only takes a blood sample, but also scans the whole body at the same time. The reason for sending both is simple. To understand a complex system, it helps to measure it in place and also watch it from a distance. Parker samples the solar wind before it has had much time to evolve. It feels the magnetic fields, the density, the temperature of the plasma near its source. Solar Orbiter watches the surface and atmosphere and connects those measurements to visible structures like coronal holes, active regions, and small-scale jets. When a gust of solar wind washes over Parker, scientists can often trace it back to a feature in Solar Orbiter's images and ask what kind of engine produced it. One of the most intriguing discoveries from Parker has been the presence of sudden kinks in the magnetic field, now nicknamed switchbacks. As the spacecraft flies through the inner heliosphere, it sometimes passes through regions where the field lines briefly flip direction, then flip back again. These are not simple waves. They seem like pieces of the magnetic field that have been bent back on themselves, as though someone had grabbed a stretched rubber band and flicked it. The plasma in those regions also behaves differently, suggesting that switchbacks may be an important way energy and momentum are carried outward. The origin of these switchbacks is still being debated. Some models suggest they might form when concentrated jets of plasma burst out from the lower corona and propagate outward, dragging field lines along. Others suspect they are created by turbulence in the expanding wind itself, a natural consequence of many interacting waves. What matters for our story is that Parker has handed us a new kind of structure to explain, something we never would have guessed from measurements taken only here near Earth. Each switchback is both a puzzle and a clue, pointing back toward whatever processes are shaping the wind close to the Sun. Solar Orbiter has been busy revealing its own surprises. With its high-resolution extreme ultraviolet cameras, it has imaged the solar surface and low corona in unprecedented detail. In some of those images, tiny bright points and flickers have been seen, so small that earlier instruments would have smoothed them out entirely. These features have been nicknamed campfires, miniature bursts of energy scattered across the surface. They may be the visible signatures of nanoflares, those hypothetical small magnetic reconnection events that could play a role in heating the corona. If campfires and switchbacks turn out to be two faces of the same deeper process, we will have connected motions in the lower atmosphere to structures in the young solar wind in a way that was pure speculation only a decade ago. Even if they are separate, they show that the Sun's outer layers are far more finely textured than our earlier images suggested. What looked like smooth loops and arcs from a distance now resolves into forests of tiny bursts and kinks. It is a little like zooming in on a forest from orbit and discovering that each tree is wrapped in vines and teeming with insects. Beyond fields and flares, these missions are also mapping the dusty environment close to the Sun. The inner solar system is not perfectly clean. It contains a faint cloud of dust from comets and asteroids that have been slowly ground down over eons. As Parker swings close, its instruments can detect dust grains vaporizing under the intense heat and can sense how the density of this dust changes with distance. That data helps refine our understanding of how sunlight and solar wind shape the distribution of dust, and how that dust, in turn, absorbs and re-emits energy. All of these detailed measurements feed into a broader goal. We do not just want to understand the Sun for its own sake, although that would be reason enough to be curious. We want to be able to say, with growing confidence, how disturbances that we see on the solar surface will evolve as they propagate outward, and what they will do to our technological cocoon when they arrive. Right now, our main early warning system for dangerous solar wind conditions sits at a point between Earth and the Sun, where gravity and orbital motion balance. The L1 point. Spacecraft there can sample the wind and give us perhaps half an hour to an hour of warning before a blast reaches Earth. That warning is better than nothing. It allows grid operators to adjust voltages, satellite controllers to put craft into safer configurations, and airlines to reroute polar flights if needed. But it is not much time. For a truly extreme event, we would like to know a day in advance, or several days, not minutes. To get there, we need to improve our ability to read the signs on the Sun itself. Which active regions are likely to produce large eruptions? How fast are coronal mass ejections moving when they leave? How will they interact with the background wind on their journey? Parker and Solar Orbiter are giving us the ground truth we need to calibrate those forecasts. Think back to the last time you saw photos of a big aurora storm lighting up the night side of Earth. The colours and curtains were only the visible edge of a chain that began with a magnetic twist in the corona and a burst of plasma launched into space. Until now, many of the links in that chain were filled in by models and best guesses. With in situ data from closer and closer to the Sun, we are starting to replace guesses with direct measurements. That means our space weather predictions can gradually move from art towards science, from rough estimates toward more reliable guidance. There is a more philosophical dimension to these missions as well. We have sent probes past all the planets, landed on comets and asteroids, and dropped landers through alien atmospheres. Flying into the corona forces us to think differently about what counts as the edge of an object. The Sun has no solid surface. There is no place where you can plant a flag and say, "We have arrived." There is only a gradient of heat, density, and magnetism that gradually gives way to the thin plasma of interplanetary space. Parker's designers had to choose a definition of touch, a boundary where sampling the wind could still be said to be sampling the corona itself. When Parker crossed that boundary for the first time, scientists described it as flying through a region where the plasma was still magnetically connected to the sun in a closed way, rather than swept out into the open solar wind. The probe passed through structures that seemed to be magnetic canyons and valleys, rather than the more uniform outflow farther out. For a brief time, it was not just near the sun, it was inside a part of its atmosphere that had never been visited. No one looking at those first plots of data could miss the sense of crossing a threshold. If you strip away the technical language, what we have done is send a fragile bundle of metal and electronics into a region of space that generations of humans thought belonged only to myths and gods. We have watched it skim past a star at distances that would have vaporized any earlier craft. We have recovered data and used it to challenge long-standing ideas about how the corona and solar wind behave. That is a remarkable widening of the human vantage point. It is also a reminder that the forces shaping our lives do not care whether we have visited them or not. The sun was flaring and breathing long before our probes arrived, and it will go on doing so long after they fall silent. As you imagine that small, shielded spacecraft carving its way through the inner corona at hundreds of kilometers per second, it is worth asking what we intend to do with the knowledge it is bringing back. Will we redesign our power grids with this new understanding in mind? Will we harden satellites, diversify communication routes, and treat space weather forecasts as seriously as we treat hurricanes and cyclones? Or will we file the discoveries away as beautiful curiosities, while leaving the systems that feed and connect us as exposed as ever? Because as daring as it is to fly into the edge of a star, there is an even more uncomfortable experiment we have not yet run on purpose, but which history tells us will happen again at some point. What really happens when the sun launches one of its rare, enormous storms straight at a planet full of electronics? And that planet is ours. When the sun launches one of its big storms, it does not look dramatic from here at first. Days earlier, somewhere above an active region, a twisted rope of magnetic field has snapped and hurled a cloud of plasma into space. That cloud, a coronal mass ejection, expands as it flies outward, carrying embedded magnetic fields and charged particles. Most of the time, these clouds miss us and wash past harmlessly. Every so often, one is aimed almost straight at Earth, and then our quiet blue world suddenly finds itself in the path of a moving piece of the sun's atmosphere. As the cloud approaches, it ploughs through the slower solar wind in front of it and piles up material, like the bow wave of a ship pushing through water. That piling up forms a shock, a sharp front where conditions change abruptly. When that shock reaches Earth, it compresses our magnetic field, pushing the day-side boundary closer to the planet and stretching the night side farther out. The impact shakes the entire magnetosphere like a bell. If the magnetic field inside the solar cloud is oriented in the wrong way, it can hook into Earth's own field and start a much deeper transfer of energy. Inside the magnetosphere, those disturbances drive currents that swirl through space and close through the high atmosphere. They energize particles, thickening the ring of charged particles around the planet and sending some spiraling down along field lines toward the poles. When those particles slam into molecules in the upper atmosphere, they make them glow. The result is aurora, the shimmering curtains and arcs that people travel far north or south to see. During a truly big storm, that glow can spill far from the poles, turning the skies above places that almost never see auroras into rippling sheets of green and red. The strongest such storm in the historical record arrived in late summer of the year 1859. A British astronomer named Richard Carrington was sketching a large sunspot group on the solar disk when he saw something startling. Within that dark blot, two intensely bright patches flared into existence, blazed for a few minutes and then faded. At the time, no one had a well-developed theory of solar flares, but Carrington knew he had seen something unusual on the sun itself. Hours later, the night side of Earth lit up with auroras so bright, people reported reading newspapers by their glow. Those lights reached far into the tropics, painting the skies of places like the Caribbean with colours locals had never seen. At the same time, the telegraph systems that represented the cutting edge of communication technology began to behave strangely. Operators received shocks when they touched their equipment. Sparks leapt from components. In some cases, telegraph lines carried so much induced current from the storm alone that messages could be sent even after power supplies were disconnected. In other cases, equipment caught fire. The world had been given a demonstration of how a storm in the sun's atmosphere could rattle a planet-wide technological system. In 1859, that system was thin. Telegraph wires linked cities, but there were no power grids spanning continents, no satellites, no undersea data cables pulsing with traffic every moment of the day. Later storms gave a glimpse of how rising technological complexity made us more exposed. In 1921, another strong geomagnetic storm damaged telegraph systems and caused fires in railway signal equipment. In March of 1989, a less extreme storm compared to the Carrington event still managed to collapse the power grid serving the Canadian province of Quebec in less than 2 minutes. During that Quebec storm, currents induced in the long transmission lines and in the ground itself found their way into transformers. These are heavy, expensive devices that step voltage up and down in power networks. They are designed to carry alternating currents with a certain rhythm. When you add a slow, direct current on top, driven by geomagnetic changes, the transformers can saturate, overheat, and trip protective systems. In Quebec, one key transformer at a major substation failed, and the resulting cascade left millions of people without power for hours. That was from a storm we now think of as moderate on the scale of what the sun can do. The underlying physics is simple in concept, even if the details are tricky. When the geomagnetic field over a region changes quickly, it induces electric fields in the ground and in long conductors such as power lines and pipelines. Those electric fields drive currents. The longer the conductor and the more resistive the ground beneath it, the larger the induced current can be. High-latitude regions with long east-to-west transmission lines are especially vulnerable. During a severe storm, those currents can become strong enough to stress or damage many transformers at once. Now imagine applying the same principle to a modern world woven together by thousands of satellites, countless kilometers of high-voltage lines, and vast networks of communication cables. Satellites in low Earth orbit feel increased drag as the atmosphere puffs up. Without frequent adjustment, their orbits decay more quickly, and some may re-enter unexpectedly. Navigation satellites higher up can suffer from radiation damage to their electronics and temporary disruptions to their signals. If those signals become unreliable, systems that rely on precise timing, from banking transactions to mobile networks, can wobble. On the ground and in the air, radio communication can falter during strong solar events. High-frequency radio, which bounces off the ionosphere to cover long distances, can suffer blackouts when that layer is disturbed. Airlines flying polar routes, which often depend on such communication, may have to detour, increasing fuel use and time. Very low-frequency signals used by some navigation and communication systems can also be affected. Even simple things like satellite television or internet services can experience outages if the satellites or the ground equipment are not designed to handle sudden bursts of noise. Then there are the undersea cables that carry much of the world's internet traffic between continents. The optical fibers inside them are mostly immune to geomagnetic effects, but the repeaters and power supply lines that keep those fibers working are not. Long cables rely on constant power fed along their length. Geomagnetically induced currents can, in principle, stress that system as well. Researchers have pointed out that a severe storm could, in the worst case, disrupt not only regional grids, but also some of the backbone connections that tie continents together online. One of the most sobering parts of this picture is how custom and slow to replace some of the vulnerable hardware is. Large power transformers are not like light bulbs you can swap at a hardware store. They are bulky, often built to order, transported slowly, and installed with care. In normal times, utilities might have a few spares for critical nodes. In a scenario where dozens fail across a continent, waiting times could stretch into months or longer. In that gap, people would be trying to live modern lives without reliable power over wide areas. It is hard to turn that into a concrete image, because we have never really experienced it at scale. You can start by recording what it feels like when a storm knocks out power to your city for a day. Traffic lights go dark. Refrigerators sit silent. Mobile towers lose backup power after a while. Payment systems fail. Now extend that beyond a day, and beyond your city, to regions where repair crews cannot simply swap a component and move on. Water treatment plants would be improvising, supply chains would stutter, hospitals would lean on generators until fuel began to run short. Economists have tried to estimate the cost of such an extreme space weather event and have come up with numbers in the many trillions of dollars for a large industrial region, depending on assumptions. The figures are less important than the shape of the impact. It would not feel like a single dramatic disaster that hits and then recedes. It would feel like a deep, rolling disruption that tests how much redundancy and flexibility our systems really have. The fact that we have sailed through the satellite age without such an event so far is a stroke of luck, not a guarantee. You might reasonably ask how likely a storm on the scale of the Carrington event is in any given decade. Studies that look at historical records, ice core data, and observations from other stars suggest that such extreme events are rare on human timescales, but not vanishingly rare. Rough estimates put the chance of a Carrington-level or larger storm hitting Earth as something like a few in 100 over the course of a century. That is uncertain, but it is not zero. It is enough that planners who think in terms of infrastructure lifetimes and national risk are paying attention. Right now, our main warning tools give us limited lead time. We can see active regions rotate onto the visible solar disk days before they face Earth. We can watch them develop and judge whether they seem capable of producing large eruptions. We can monitor for flares and fast coronal mass ejections leaving the Sun. For some of those events, coronagraph images let us estimate their speed and direction and predict an arrival time 1 to 3 days later. But the crucial detail that determines how strongly the storm will couple to Earth's magnetic field is the orientation of the magnetic field inside the cloud, and that is very hard to know until the cloud is nearly upon us. Spacecraft at the L1 point, about 1.5 million kilometers upstream from Earth, measure that orientation directly when the cloud reaches them. From there, the storm front takes tens of minutes to an hour or so to sweep past and hit Earth's magnetosphere. That is when we know for sure whether we are about to experience a mild geomagnetic disturbance or something far more intense. For some purposes, an hour is enough to take basic protective action. For others, it is painfully short. If we want days of confidence, we need better models, more probes closer to the Sun, and a deeper understanding of how the solar atmosphere shapes those clouds in the first place. There are promising ideas on the table. Power companies can design networks with more smaller transformers instead of fewer huge ones, making the system less brittle. They can install devices that block slow, geomagnetically induced currents from entering transformers. Satellites can carry hardened electronics in redundant systems. Airlines and navigation providers can plan flexible routes and backup procedures for times when polar communications will be stressed. Governments can treat extreme space weather as a national-level risk in the same way they now treat large earthquakes or tsunamis. Some countries have already written space weather into their national risk assessments and begun modest steps in that direction. Others have barely started. It is easy to see why. Unlike a storm cloud on the horizon, the Sun looks the same to your eyes whether it is about to launch a major eruption or not. There is no dramatic wall of water to capture the imagination, no crack in the ground. The threat is invisible and statistical. It lives on timescales longer than election cycles and news cycles. That makes it the kind of problem human institutions are often worst at addressing. For you as an individual, the most helpful shift may be mental rather than technical. It is the recognition that sunlight on your skin, the gentle warmth and brightness you feel, comes from a star that can also rearrange currents in the mantle beneath your feet and electrons in the wires above your head. The same processes that paint auroras over quiet northern lakes can, in their more intense forms, knock out parts of the systems that feed you information, food, and water. We do not need to panic about that. Panic rarely produces good engineering. But we do need to fold the sun's moods into the way we think about resilience. There is an irony in all of this. At the very moment we are waking up to how vulnerable we are to the sun's anger, we are also becoming more ambitious about using its energy. Solar panels spread across rooftops and deserts. Solar thermal plants concentrate light to heat fluids and turn turbines. Some dream of vast solar power stations in orbit, beaming energy down on microwave or laser beams. Futurists imagine structures that would surround a star with swarms of collectors, capturing a significant fraction of its output to feed unimaginable numbers of minds and machines. In other words, we are beginning to move from simply enduring what our star does to trying to harness it more deliberately. That shift raises its own questions. How far can a civilization like ours go in relying on a star without being overwhelmed by its variability? Can we learn to ride out its worst storms while tapping more of its steady output to replace the stored sunlight in fossil fuels we have been burning so quickly? And in the long run, what does it even mean to say that we could own a share of a star's power when we still struggle to predict its next major mood swing? There is a strange moment in the growth of any civilization when it stops seeing its star as a distant backdrop and starts seeing it as infrastructure. For most of our history, the sun was something to endure and to worship, a giver of seasons and harvests and droughts. Now we bolt dark blue panels to rooftops and deserts and quietly plug our homes and data centers into its light. We talk about gigawatts and terawatts instead of dawn and dusk. Somewhere along that curve of ambition, a new idea appears in our heads. If a thin film of silicon and glass can power a city, what would it mean to wrap an entire star in machines and treat it as our primary power plant? The physicist Freeman Dyson once suggested a thought experiment. If you let a technological species keep growing its energy use for long enough, eventually the waste heat has to go somewhere obvious. One way to cope would be to build a swarm of collectors and habitats in orbit around their star, each one sipping a fraction of the light and turning it into work and then heat. From far away, that star would look dimmer in visible light and brighter in infrared, wrapped in a cloud of warm structures. This was not a blueprint so much as a way to ask what very old, very capable civilizations might look like if we searched for them. The numbers behind that vision are dizzying. The sun outputs roughly 10 to the power of 26 watts of power every second without pause. Human civilization at the moment runs on a tiny fraction of that, even after 2 centuries of industry and growth. A Dyson-style swarm would not need to catch all of the light to surpass anything we can imagine now. Even capturing a thin shell of it would mean energy budgets big enough to move planets, reshape orbits, and run simulations of entire worlds. From that vantage point, worries about fuel shortages and blackout days would seem quaint. It is tempting to imagine such a future and draw a straight line from our current rooftop panels to rings of orbiting collectors and then to full stellar swarms. In practice, the line is anything but straight. Building and maintaining even a modest ring of solar power stations in space would require mining on asteroids, factories in orbit, millions of launches, or cheap new ways to climb out of gravity wells. A true swarm would require entire worlds to be taken apart for raw material. Each step would bring its own risks and political tensions, long before anyone had to worry about reshaping a star's environment. There is another subtle cost. The more tightly you tie your civilization's metabolism to a single star, the more you share its fate. A swarm of collectors might make you robust against local power plant failures. It would not free you from stellar cycles and storms. Extreme flares and mass ejections would still thread through your infrastructure, perhaps in even more complicated ways. If you did not want your habitats and transmitters to be sandblasted by particles and radiation, you would need shielding on scales we can barely picture. Owning a star's output would mean owning its anger, not just its gentle glow. At the same time as these grand visions circulate, people sometimes propose a much more modest-sounding use for the sun. If we are struggling with long-lived nuclear waste on Earth, why not simply throw it into the star and let it be destroyed? On paper, this sounds clean and decisive. The Sun is vast. The mass of our waste is tiny compared to it. From a chemical and radiological perspective, the waste would indeed disappear into the solar plasma without a trace. The trouble, once again, is not in the chemistry. It is in the orbits. Right now, the material we want to get rid of sits deep in Earth's gravity well and shares Earth's sideways motion around the Sun. To send it inward, you have to cancel most of that sideways speed. That means thousands of meters per second of velocity change, far more than what you need to escape Earth into a typical interplanetary trajectory. Every extra meter per second of required change translates into exponentially more rocket fuel. When engineers run the numbers, they find that shooting a payload into the Sun demands enormous energy. It is much easier to throw something outward, into the outer solar system or interstellar space, than to drop it straight down the well. You might try to cheat by using planetary gravity assists the way Parker Solar Probe does, letting Venus shave away orbital energy over many loops. But those maneuvers require years of careful navigation for each payload. They only make sense for spacecraft that are themselves priceless scientific instruments. Turning every canister of waste into a multi-year precision mission would be absurdly expensive. Worse, each launch that fails on the way up risks spreading radioactive material in the atmosphere or across land and sea. The very act meant to make the problem vanish could create dozens of smaller disasters along the way. For now, the most realistic strategies for handling nuclear waste look inward rather than outward. We can concentrate it, vitrify it into stable glass, and bury it deep in carefully chosen rock formations where water moves slowly and erosion is minimal. We can design repositories to remain safe for spans of time much longer than any human institution has ever lasted. None of that feels as satisfying as imagining waste plunging into a star and being unmade. But it is grounded in the physics and engineering we have, not the orbits we wish we could easily change. In a sense, both the Dyson Swarm dream and the Throw It into the Sun dream highlight the same lesson. We are good at making sketches where the Sun is simply a bright target in the sky that we can paint with arrows. The real solar system is a ballet of moving bodies tied together by gravity. Any serious plan to own more of our star's power, or to use it as a trash incinerator, has to deal with that dance step by step. The warm circle we draw in our minds is not how the Sun actually appears in our equations. If there is one place where we have learned to use the geometry of the Sun with real subtlety, it is in the art of creating and watching eclipses and occultations. When the Moon passes in front of the Sun from our point of view, we get those rare minutes of totality when the corona stands out in all its delicate structure. By placing telescopes along the narrow path of the Moon's shadow, scientists can sample different slices of the corona and watch how features evolve in real time. Artificial eclipses, created by coronagraphs that block the bright disk with an internal mask, let us do something similar from space day after day. We use occultations in more creative ways as well. When a planet or a spacecraft passes behind the Sun from our vantage point, its radio signal must pass close to the solar limb. The way that signal is bent and delayed by the hot plasma tells us about the density and structure of the corona along the path. During transits, when planets pass in front of the Sun, we can watch for tiny dips in light at specific wavelengths to learn about any gas in their thin atmospheres. The same trick is used on distant stars to study exoplanets, turning the alignment of disks and spheres into a tool for remote sensing. There is an elegance in this use of shadows and alignments. We live in a system where the sizes and distances of Sun, Moon and Earth just happen to create perfect total eclipses. We orbit at a distance where the Sun appears large enough to dominate our sky, but small enough that other bodies can still cover it. Those coincidences are not required by physics. They are historical accidents of orbital evolution, yet we have learned to read them, to turn them into experiments that peel back layers of the solar atmosphere and test our theories. It is as if nature gave us a few rare geometry problems and invited us to solve them with light. Looking forward, the geometry will change in grander ways. The Sun is about middle-aged in stellar terms. Over the next billion years or so, it will slowly grow brighter as hydrogen is used up in the core and the structure readjusts. That gradual increase in luminosity will push the habitable zone outward. At some point, the delicate balance that keeps Earth's surface water liquid will tilt. Oceans will evaporate more quickly. Weathering of rocks will change. Greenhouse gases will be drawn down in different ways. Long before the Sun turns into a true red giant, our planet may become a steamy, less friendly place for complex life on the surface. On longer timescales still, billions of years from now, the core will exhaust its central hydrogen, and the Sun will swell into a red giant, engulfing Mercury and Venus, and likely scorching or even swallowing Earth. After that phase, it will shed its outer layers, leaving behind a dense white dwarf that slowly cools over trillions of years. These events lie far beyond any human planning horizon. They are cosmic background, the timetable written into the physics of all stars of this mass. Yet even knowing that deep future has a subtle effect on how we see our present window. We find ourselves living in a comparatively narrow slice of time when the Sun is bright and stable enough for complex life and for civilizations like ours, but not yet so bright that the climate tips into runaway greenhouse. Our ancestors had no way to know that. They lived inside the present moment and its myths. We have equations and spectra and models that let us place our current age on a long stellar timeline. It is hard not to feel both lucky and slightly unsettled. Lucky because the conditions under which we evolved are not guaranteed to last forever. Unsettled because we are changing that climate ourselves much faster than any natural trend would demand. So when we talk about harnessing more of the Sun's power, or shielding ourselves from its storms, or burying our waste instead of flinging it into the sky, we are really talking about how to behave during this brief and generous chapter. Do we treat the star above us as a resource to be squeezed without thought, or as a partner whose patterns we study and respect? Do we design our infrastructure as if the Sun will never surprise us? Or do we build with the understanding that even mild stars have moods that can shake a technological world? It is not hard to picture a distant future in which human descendants, or whatever follows us, live scattered through the solar system, perhaps in habitats orbiting closer to the Sun or drifting further out. From those vantage points, they will watch the star change slowly and watch the record we have left in rocks, in isotopes, in bits of junk orbiting Earth. They will see how quickly a young technological species burned through stored sunlight in the form of fossil carbon, how it learned, if it learns, to switch to the direct flow from the star instead. By then, if we are fortunate and wise, the relationship with the Sun will have shifted again, from awe to science to engineering to something like stewardship. We will still not control the star, no civilization ever will, but we might learn to live in rhythm with it, to ride out its storms without catastrophe, to use its light without poisoning our own nest. Every solar panel, every weather satellite, every probe that dips into the corona is a small step in that direction, a quiet answer to the question of whether we intend to stay. The light that wakes you each morning has travelled for thousands of years inside a star and minutes across space to reach your skin. It carries the story of nuclear reactions, magnetic storms, and ancient geometry. What story will it carry back out into the galaxy when it reflects from our cities and machines? When distant observers someday see the faint, flickering signature of Earth and wonder what kind of creatures once lived in this orbit around a modest yellow star?